Everywhere I go, I'm hearing motherfuckers trying to steal my flow, but it ain't no thing, cause see my nigga Coolio put me up on the game when I step through the door. You know, some of these niggas is so deceptive, using my styles like a contraceptive. I hope you get burnt, seems you haven't learned. It's the knick-knack paddywhack, I still got the...
Problem 2229 invites us to apply Gauss's law 3 times. We have this sphere and we can distinguish 3 different regions. The inner cavity where there is no charge, the central part where we have evenly distributed charge Q, and then the outside region, outside the whole sphere. So first, in part A, where R is less than R1, so we are somewhere here. Let's draw our Gaussian surface at some distance R, and our Gaussian surface is of course going to be a sphere because this is a spherical symmetric case. So the electric field, if there is any, is constant on this surface. Gauss's law states that the electric field dot product by dA, the surface directional vector, and this whole thing is of course the electric flux, equals the Q enclosed within this surface. Within this surface there is no charge, so this one is 0, which means that also equal E, the electric field must be 0. In part B, we are considering the area or the volume R greater than R1. But smaller than the outer surface R0. We will again pick our Gaussian surface to be some sphere at this distance. And to get started, we need to define something called the charge density, because the charge in this region is uniformly distributed. We define our charge density as the total charge in the sphere divided by the volume where there is charge. So the volume where we have charge. So where do we have a charge? We have charge between these in this shell that has outer volume of 4/3 pi R0 to the cube, that's R0, minus the cavity, the volume of the cavity. The radius there is R1. So we get Q over 4/3 of pi R0 squared minus R1 squared. So that is our charge density anywhere within the shell. Next, we have to define or find out how much charge is within our Gaussian surface. So we have charge only within this shaded region. So what is the charge enclosed there? It's going to be the volume of this thin shell where we have charge. Let's call it the volume R, times the charge density we just calculated. So what is the VR? It's going to be the outer sphere minus the cavity. So 4/3 pi R, we are at distance R from the center cubed, minus the volume of the cavity, which is R1 to the 3rd power. And then we have our charge density from here q times 4/3 of pi r0 squared minus r1 cubed, r1 cubed. So this cleans up, these 4/3 of pi's disappear, and we are left with q times r to the third minus r1 to the third divided by r0 third minus r1 third. Now that we know our enclosed charge, we are ready to apply the Gauss's law to find out the electric field. So is Q enclosed divided by E0. Again, this electric field is constant at this surface, so it pops out of the integral, and the integral becomes just the total area of the sphere, so E times A. And now we have our Q enclosed from here. Let's do it this way, E0. And because we want to solve for the electric field, it's going to be Q enclosed divided by A times E0, where A is the surface of our, or the area of our Gaussian surface. So Q enclosed from here, Q times R to the third minus R1 to the third divided by R0 to the third minus R1 third. Then we have these terms. The area of the sphere at distance r, 4 pi r squared times E0. And in fact, here we have 4 pi times E0 is the constant k. So we get Q times r to the third minus r1 third divided by r0 to the third minus r1 third, and we are left with k over r squared. In the last case, the radius and a Gaussian surface is outside the actual sphere, so we are operating somewhere here. In this case, the Q enclosed is all the Q in the sphere, so it's simply Q. Then Gauss's law states Q over E0. In this last step, I want to make sure or want to make clear what happens with this one. So as I stated earlier, on this sphere at our Gaussian surface, the E is always the same. So E is constant. It doesn't depend where on the surface you are, it's always E. So therefore, the E itself has nothing to do with integrating over the surface. The E is constant. So therefore, the E comes out from the integral, and we are only left with surface integral over the whole surface. Which means that the value of this is just the area of the sphere, which in our case is 4 pi r squared, and then q over E0. And solving again for E, we get q over 4 pi E0 r squared, where 1 over 4 pi E0 is same as k, and we get the familiar result for point charge. So essentially what this tells is that the electric field outside the sphere acts like it would, if all the charge would be concentrated in the circle, or in the heart of the circle, in one point. So once we are outside the sphere, it doesn't matter if the charge has been distributed in this way or if it will all concentrated in the center. So these are all the different results for the 3 different cases. First one, inside the cavity where there's no charge. Second one, somewhere within the shell where we have charge. And the third case, outside the whole sphere.
Still east side till I die. YXY as the world keeps spinning to the DOWG. Why?